to our first lesson of chapter 5, which is graphing sine and cosine functions. So we've got a little outline here of what these functions look like, and we're just going to go through how they are generated. We did this very briefly at the end of chapter 4, so we're going to go through it a little bit more slowly. This set of notes is probably going to take a little bit longer than many of the other sets that we're used to doing. So first, a couple reminders from chapter 4. I'm just going to draw them at the top of the page here. So we talked about a quadrant system, and we talked about radians, and we talked about how if we were looking at the positive x-axis where we would normally see 0 degrees or 360 degrees, this is now 0 radians or 2 pi radians. Going a quarter turn around the circle, this would be 90 degrees or pi over 2 radians. Over to the left, we would have pi radians where 180 degrees would go. And at the bottom, we would have 3 pi over 2 radians where 270 degrees would go. We had a couple special values, which was if we were on the x-axis at all, sine of theta here is equal to 0, and sine of theta over on the left x-axis is also 0. So that might be sine of 2 pi, sine of 0. We could keep going many circles around our quadrant system and get to 5 pi or 6 pi or 7 pi. All of these sine values would be 0 for those angles. Okay. On the positive x-axis, we talked about how cosine of theta was equal to positive 1. And on the negative x-axis, cosine of theta was equal to negative 1. On the y-axis, the reverse is true. On both the positive and negative y-axis, cosine is equal to 0. And on the positive y-axis, sine is equal to 1, and the negative y-axis, sine is equal to negative 1. We also know that if we are between 0 and pi over 2, everything is positive in this quadrant. If we're between pi over 2 and pi, only sine is positive. If we're in quadrant 3, then only tangent was positive, and in quadrant 4, between 3 pi over 2 and 2 pi, only cosine was positive. So this is going to help us draw in our curves here. Now, we also know that it's not possible, if we think about a triangle, with an angle down in the corner, we know we have opposite, adjacent, and hypotenuse. We know that for sine, we know that sine is equal to opposite over hypotenuse. And since the opposite is always smaller than the hypotenuse, the biggest value for sine is 1. Because there's no way we could have something like sine theta equals 5. If sine theta was equal to something like 5, that means the opposite would have to be bigger than the hypotenuse, which is not possible. We did see that sine could equal 1 on the y-axis, the positive side, and that was if we thought about that as like a collapsed triangle, where essentially the adjacent side was no longer there. The same is true for cosine. Cosine is adjacent over hypotenuse. And again, we cannot have a value bigger than 1 for our cosine because that would mean adjacent is bigger than your hypotenuse. So when we graph these, what we're really doing is we're graphing y equals sine x or y equals cosine x. So again, we have our usual x-axis. So those are all angles that we're plugging in. Okay, and y would be all of our ratios. So things like 1/2, 1 over 2, root 3 over 2, all of those things that we saw in chapter 4. Okay. So if I'm graphing ratios and we know our biggest ratio is 1, so the opposite over the hypotenuse or the adjacent over the hypotenuse is a ratio. We know our biggest value is 1. We can see the dots here that have sort of been sketched in for us go as high as 1. So that's going to be on our x-axis, and they go as low as -1. If we're trying to graph sine, we also know from our quadrant system that we drew up above here, we know that sine is 0 on the positive x-axis and the negative x-axis. So if I think about going around in a circle, starting on our positive x-axis and going counterclockwise, the first time I'm going to equal 0 again is at pi. So if I read my graph left to right and I start heading over to the right, that would be like going in a positive circle around our quadrant system. So the first time I'm going to hit 0 again is at a value of pi. And then if I keep going around my circle, the next time I'm going to hit 0 again is back when I've completed a full circle, which is at a value of 2 pi. And if I kept going, again, I'd get to 3 pi back on the negative x-axis, and again at 4 pi. If I did a backwards circle, I would end up at negative pi, going in the backwards direction. We also know from chapter 4 that sine theta is equal to 1 if our angle is pi over 2. So we're going to draw that in on our axis. We can see that our value would be up at 1 for pi over 2. And everywhere between 0 and pi, if I wanted to draw this in here, everywhere from 0 all the way to pi, sine is positive. So in the top 2 quadrants. And then in the bottom 2 quadrants, we know that sine is negative. So that's why this curve here makes sense. Now, I also know that I reach a value of -1 for my sine if my angle was 3 pi over 2. So hopefully you'll notice you have a pi over 2 and then a 3 pi over 2. Our next peak is going to happen at 5 pi over 2 and then 7 pi over 2. And this could keep going if we wanted. If we went in the opposite direction, our first part we would come in contact with a peak be negative pi over 2. So hopefully we can see our domain. We can go left and right forever. Our range, our smallest value is -1, and our biggest possible value is 1, which means our minimum is -1 and our maximum is 1. Zeros, remember, are just x-intercepts. So our x-intercepts, hopefully we can see our x-intercepts are happening at all the pi's. Okay, so our x-intercepts, we've got one over here at -pi as well. Our x-intercepts here are at -pi, 0, pi, 2 pi, 3 pi, etc. So the nice, neat way of writing this is at all the pi ends where n is an integer. So if n was 1, we'd be at 1 pi. If n was 4, we'd be at 4 pi. If n was -1, we'd be at -1 pi. So this just says that n is an integer. Again, you can use an I instead if you would like. All right. Now, period is basically asking us how long does it take to complete one full cycle? So if I were to start going around our curve, when would I get back to my starting point? So our starting point that we like to think of for sine is at the origin. We're at 0, 0 and we start sort of like mid curve. And so the question is, well, when do I get back to that same point? And if I take a look, if I start here, I'm getting back to that same sort of starting point right here at 2 pi. So this is one cycle or one period. Okay, so our period is 2 pi, which again we talked about in chapter 4. fact that if you went around your quadrant system, you had to complete a full circle, a full rotation around the quadrant system before any of your values started repeating themselves again. Now we can use the same logic to complete our cosine graph. So again, x, this is angles. So things like pi, 2 pi, 3 pi, etc. And y is ratios. So if we think back to our quadrant system again, we know that if we're on the positive x-axis at 0, our cosine value is 1. And we get back to positive 1 again after we've gone around a full circle. We hit negative 1 if we're on the negative x-axis, which was an angle of pi. And we know that cosine is 0 on the y-axis. And so the first time, if we go around our quadrant system again, the first time we're going to get cosine being 0 is up here at the y-axis, which was a value of pi over 2. Okay, so we started over here at 1, we rotated, we were equal to 0, then we had negative 1, and then we get back down to 0 at 3 pi over 2. So the next time that we cross the x-axis and we're at 0 is going to be at 3 pi over 2. And so if I draw this in, this is what this looks like. And again, this should make sense. From 0 to pi over 2, cosine is positive. And then from pi over 2 to pi, cosine is negative. It's still negative down here in quadrant 3, and then it's positive again at the end. So that matches what we just drew. It's positive here, and then negative, and then positive again. So cosine basically starts at its maximum or at its peak, crosses the axis, dips down to a minimum, and then ends up back at the peak again. Okay. And again, we can think, okay, if we keep going around the circle, by the time we get back up to the maximum, we will have had to do a full circle. Our minimum would have been on the negative x-axis, which would be after completing 3 pi. And again, if we follow the pattern of the pi over 2's, we've got pi over 2, 3 pi over 2. The next is going to be 5 pi over 2, and then 7 pi over 2. If I go in the backwards direction, I'm going to have negative pi over 2. I find it really hard to draw it neatly starting at the peak. So sometimes once I've drawn my points in, I start drawing from a different location. So again, our domain, I can plug in any angle I want into cosine. There's no restriction there. Our range, our lowest value is -1. Our highest value is 1. We can't go any lower or higher, or that means our adjacent is bigger than our hypotenuse. That doesn't make any sense. Our minimum is therefore -1, and our maximum is 1. And our period, again, if I start at that maximum value, the next time I reach my maximum value is over here at 2 pi. So one cycle or one period is 2 pi again. And our zeros, if we take a look at our zeros, they're at all the pi over 2's. So we've got one at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc. And again, there's a nice, neat way of writing this, which is if I start at my first one, which is pi over 2, in order to get to the next one, I have to add pi. And then to get to the next one, I have to add pi. So I can write this as pi over 2 plus pi n. So which zero I'm at just depends on how many pi's I'm going to add. But again, your pi's have to be integer values of pi's. Okay? Or you can write pi. Okay? You need to know these two graphs. Okay, so you need to know that sine and cosine have a period of 2 pi. You need to know that their ranges are from -1 to 1. You need to know that sine starts at that middle point, goes up to its maximum, then down to its minimum and back to the middle. And you need to know that cosine starts at the maximum, goes down to the minimum and back up to the maximum. These are called sinusoidal curves. All right. So if a question asks you to draw a sinusoidal curve, it's talking about sine or cosine. This means they oscillate or move up and down repeatedly from some sort of center line. So they're symmetric in that way. Okay. So we're going to try graphing these using transformations. All right. So if you recall from way back in chapter 1, if we have a function where you have a number in front of the function, this was a vertical expansion. By that number. So we just take it as we see it, okay? Or a vertical compression. If this was like 1/2, we're gonna have a vertical compression. So we're gonna graph a couple different things here. So first, we are going to wanna graph our base graph so that we have something to go off of. Our range is telling us we're going from 0 to 2 pi, so we only need to do one cycle or one period. Okay. We also need to think about how we're going to label our axes here. So I'm going to take a look at these before I start drawing them. So our first one, we've got a 3 in front. So this means we're going to have a vertical expansion by 3. So normally our highest point is 1. We expand that by 3. Our highest point is now going to be 3. Our next one, we've got 0.5. This means we're going to have a vertical expansion by 0.5 or 1/2. And the last one, we've got -2. So this is going to be a vertical expansion by 2 and also a vertical reflection. So the lowest value we're going to need to go and the highest value we're going to need to go is from the biggest expansion, which was 3. So I'm going to label my axes as every 2 boxes is worth 1 so that my 3 can still fit and my -3 can still fit. I don't need any values to the left of my axis because it's telling me my smallest x is 0. And I need to go up to 2 pi. So I might make maybe every 3 boxes is going to be pi over 2. That would work. You can spread it out more if you would like. So I'm going to draw my basic sine graph first because it says to use sine x as a base graph. So how I like to draw my sines is I am going to place all my zeros first. Now, these graphs have a nice little feature where everything can basically be broken down into quarters. So I know that sine starts and ends on my axis. It starts at 0 and ends at 2 pi. You take a look at the graph from the front, we also know it's going to cross halfway between here. I know that it reaches a maximum first, then a minimum. My maximum is halfway between the first 2 points. My minimum is halfway between the next 2 points. And I know for a regular sine graph, my maximum is 1, my minimum is -1. So if I go halfway between the first 2 points, that's pi over 2, and my maximum is 1. Halfway between the next 2 points, my minimum is -1, and I can draw this in. Now it's going to be very easy to draw my expansions here because they're all vertical expansions. So this is only going to stretch up and down. We're not stretching or compressing left to right. So that means all of my zeros stay in the same spot because 0 times 3 is just 0. But now my maximum, instead of being at 1, needs to be at 3. And my minimum, instead of being at -1, needs to be at -3. And so it's just going to stretch up so that it's 3 times as tall. The next one, we have expansion by 1/2. Again, all of my zeros will stay in the same spot because 0 times 1/2 is just 0. And then that means that our maximum, instead of being at 1, will now be at 1/2. And our minimum, instead of being at -1, will now be at -1/2. I'm going to move this 3/2 label because it's going to get in my way here. Let's put this here. And you'll see that this now looks like the red graph has been squished vertically so that it's half as tall as it was before. Okay. So you don't have to draw the basic graph every single time, but I find it very helpful. I still draw the basic graph and help. Okay. The last one, now the problem is that we have expansion by 2 and a reflection. So normally our point is at +1. We expand that, now it's going to be at +2, but if we reflect it, it should be down at -2. Our zeros are still staying in the same spot. They don't move when we change how tall this thing is because your y value is 0. So whatever I multiply it by, it stays at 0. Okay? So instead of going up first, because we've reflected it, it's going to go down first. And then our red minimum here is at -1. So if I multiply that by 2, I get to a -2, but then I have to reflect it so that it becomes +2. Okay. So the A in the front, when we're talking about sine and cosine, this is our A in front of sine x or cosine x. So for example, A sine x or A cosine x, we call that amplitude. And this is our vertical expansion or compression. So if a question asks you what is the amplitude, often you can tell that from either the graph or from function. So for example, if we were given a graph, we can literally like count how tall this graph is. Okay. We can also use this little formula that says maximum minus the minimum divided by 2, because notice how for all of these, the total height is twice as big as the number in front. So if I look at the blue one, if I look at the total height of this graph, the total height is 6, but my amplitude was 3. Okay? So for example, if I have 3 sine x, right, this means that my maximum is going to be 3. Normally it's 1. If I multiply by 3, I get a max of 3. And normally my minimum is -1. If I multiply by 3, I'm going to get -3. So if I wanted to find my amplitude, I would do my maximum minus my minimum over 2, which would give us 3 plus 3 over 2, or 6 over 2. So my amplitude is 3. So I don't really need this formula. I could have just looked and seen that there was a 3 in front and said, okay, my amplitude is 3. The other thing we're going to look at today is how our period changes. So just a reminder that if you have a b inside your function with the x, this was a horizontal expansion or compression by 1 over b. So because our usual expansion or compression, our usual horizontal distance, is 2 pi, if I expand or compress it, that's 2 pi is going to change. So if I have something, for example, like y equals sine of 5x, this indicates a horizontal compression by 1 over 5. So if my period is normally 2 pi, this means that my period is now 2 pi times 1 over 5 or 2 pi over 5. And that's where this 2 pi over b comes from. My b here is 5. So I could have just gone straight to 2 pi over 5. Okay, so we don't have to do this whole song and dance of, oh, it's a horizontal compression, but this period times the compression. If you can identify b, your new period is 2 pi over b. So we're going to try one. Okay. And notice that we've got a b value here. My b value is 4. And we need to pay special attention that this time we're not going in terms of pi, we're going in terms of 6. So if our period is normally 2 pi over b, my b is 4, so this is going to give me 2 pi over 4 or pi over 2. But our question's in degrees. So pi over 2 we know is 90 degrees. This means we'll do a whole cycle in 90 degrees. Okay? But we've been asked to use the domain 0 to 360. So since we're going from 0 to 360, question is how many of these can we fit? Well, if one is going to take 90 degrees and we have to go all the way to 360, we're going to be drawing 4 cycles. Okay. So again, we haven't changed anything else. So our normal sine function would have a maximum of 1 and a minimum of -1. We didn't change our amplitude. There's no number in front of this whole thing. Okay. We know that we have to go all the way up to 360, and we have to somehow draw 4 of these cycles where each one is 90. So choosing your x-axis values really messes some people up. What I like to think of is because I can split sine and cosine always into 4 equal chunks, okay, by doing the whole starting, ending, midpoint, max, min business. Okay? I want to figure out how can I fit 90 on here so that I can easily split 90 into 4 equal chunks. So what that means is I want maybe 4 boxes to be worth 90 degrees, or 8 boxes to be worth 90 degrees, or 12 boxes. I want to be able to split my 90 degrees into 4 chunks easily. So I don't want to make 7 boxes 90 degrees. That's not easy to split into 4. So if I do 4 boxes as 90 degrees, I have to go all the way up to 180, or sorry, to 360 here. So I wouldn't have been able, I could have done 8 boxes and I might have been able to fit as well, but I probably space. Again, I don't need to go to the left because it told me I'm starting at 0. So to draw one cycle, if it only takes 90 degrees, again, I know that sine starts at the middle point, goes up, down, and ends at that middle point. So to draw one cycle, I'm going to start at the middle point, end at 90. I know it crosses halfway, so after 2 boxes. Okay, so it crosses here halfway. And then the maximum is halfway between the first 2, and my maximum I know is 1, and the minimum is halfway between the next 2. So one cycle is going to look like this. And then I can just rinse and repeat. So the next one is going to be after another 90 degrees. I'm going to draw it in another color so you can see the other cycles. We're going to cross halfway, maximum halfway between the first 2, minimum halfway between the second 2, and drop. Finishes at 270, crosses halfway, maximum halfway, minimum halfway, and drop. Finishes at 360, crosses halfway, maximum halfway, minimum halfway, and drop. So if we compare regular sine x versus sine 4x, for sine x versus sine 4x, our amplitude of sine x is 1. Our amplitude of sine 4x is also 1. Our domain is the same for both. We're going from 0 to 360 on both of these. If I drew in sine x, it would still go from 0 to 360. Our range on both of them goes from 1 to -1 because I didn't change my amplitude, but the period is different. So your period on sine x is 2 pi, or 360 degrees. My period for sine 4x was pi over 2, or 90 degrees. So this is what changed. And it's a quarter as big as it was before because sine 4x would be a horizontal compression by 1/4. Okay. So again, I'm going to try one more of these. So here, my b is 1/2. So I need to determine my period. As soon as I change b, I need to determine my period. And this is going to be 2 pi over 1/2, which gives me 4 pi. The domain they've given me is 0 to 4 pi. So I'm only going to fit in one cycle. Or one period. I'm graphing cosine. So for cosine, we can still use some of this half business that we've been using for sine. For cosine, we start up at our maximum, we go down to our minimum and back up to our max. Okay. And so whatever our maximum is, we're going to start and end there. Our minimum is halfway. Okay. And then our x-intercepts are our other half points. So I know that my maximum and my minimum are still 1 and -1. So as long as my y-axis I can reach there, we're good. We have to go all the way up to 4 pi. And again, I know I want to be able to split into groups of 4. So as long as I go at least 4 boxes, I'm good. I probably want to go more than 4 boxes just so that it doesn't look completely ridiculous. So maybe I'll do 4 boxes is worth 1 pi. So if I graph just the original cosine, I'm going to do cosine x in red here. If I do just the original, I'll show you how this chunking it into quarters works. So I'm going to start and end. My regular period is 2 pi. So if I start and end at the maximum, it's at 2 pi. Halfway between is our minimum, which is going to be at pi. And then halfway between each of these is where we're going to cross the axis. So we are not drawing this in like a V. This is a curve. I hate drawing it from the top. I usually start from the bottom here and go like this and then connect the other half because my sided on this. So if I use the same logic to graph my new one, I'm going to do y equals cosine 1/2 x in blue. And my period for this is 4 pi. So again, my maximums did not change. I'm going to start at my maximum and end at my maximum at 4 pi. My minimum is halfway, which is at 2 pi. And I'm going to cross my axis halfway between each of those. Again, I hate drawing it from the first value on the left, so I usually start from one of the middle points and then, okay. Now, this has been a lot of information so far. So if you are feeling like this is a lot for today, you could stop there and try some practice questions and keep going another day. Or if you're feeling like, nope, this is all right, you're welcome to continue on. What we're going to do next is graph with both of these changes happening. So a change in period and a change in amplitude. Okay. So the 3 in the front, this is our A value. And this is going to change our amplitude. So this means our maximum is now 3 and our minimum is now -3. The 4 is our B value. This changes our period. So our period is usually 2 pi. Now it's going to be 2 pi over B, which for us is 2 pi over 4 or pi over 2. It says at least one cycle. I'm going to do 2 or 3. Again, if I have to go for at least one cycle, I need to make sure my x-axis goes at least up to pi over 2. But again, I want to be able to split this up nicely. So I'm going to make 4 boxes worth pi over 2. We could have also done 8 boxes being pi over 2. That would work as well. So that means the next one's going to be pi, and then I'd have 3 pi over 2, and then I'd have 2 pi. I know on my y-axis I have to go at least up to 3 and at least down to -3. You do not have to do 2 boxes here. You could just have 3 boxes be worth 3 units. That's fine. Your graph will just look slightly different than mine. Now, again, I know that my basic sine graph looks like this. I know I start and end at the midpoints, which for us is still on the x-axis. Okay. We know that the period's pi over 2, so I need to start and end so that I'm starting at 0 and ending at pi over 2. I know for sine, I cross halfway. My maximum halfway between the first two, but my maximum is now 3. My minimum halfway between the next two, it's now -3. It's going to look like this. And if you spread yours out more on the x-axis, like if you had 8 boxes be pi over 2, yours will look more stretched out side to side. The key is you start and end at the right spots. If I wanted to draw in another cycle, which I do not have to do, it said at least one, but if I wanted to draw another one, I'd end another pi over 2 to the right, which is at pi. I would cross halfway, maximum halfway, minimum halfway, and draw. If I did another one, again, I'm going to end at 3 pi over 2, cross halfway, maximum halfway, minimum halfway, and draw. So we're fitting in more cycles than we usually would. Normally, if we went all the way up to 2 pi, we would fit one cycle of sine. But for us, we would have fit in 4 if we keep going. Okay. So one cycle is in blue here. So I find it easiest to mark the start and the end of one period and split it into 4 sections and then mark major points. So again, this one we're going to do 2 cycles. So we've got our amplitude at the front. Amplitude is equal to 3. Okay, so this is a vertical expansion by 3 and a vertical reflection. We've got a B value of 2. So our period is usually 2 pi over B, or 2 pi over 2, which gives us pi. Again, we want to be able to split into 4 nice sections. And we know that our maximum and our minimum are dependent on our amplitude. So normally our max is 1, now our max is going to be 3. Normally our minimum is -1, now it's going to be -3. And we need at least 2 cycles, which means we need to go up to at least 2 pi on our axis. Or if we want, we could do 1 cycle on the right and 1 cycle on the left. So I'll show you what each of those look like. And because we want to split into 4 sections, we want to make sure that our pi is worth at least 4 boxes, but pi could also be 8 boxes or 12 boxes. Any multiple of 4 will work for us. I'm going to do 8 boxes just to show you what it looks like a little bit more stretched out. And then that means this one here is actually a pi over 2. And then another 8 boxes would be 2 pi. If I wanted to keep going, I could do another 8 boxes. That would be 3 pi, etc. If I go the left direction here, that means 8 boxes to the left is going to be negative pi. Again, I need to make sure I can go up to at least 3 and down to at least negative 3. And we know that usually cosine starts at a maximum, goes down to a minimum and back up. The difference here is we do have a vertical reflection. So what that means is if we have a vertical reflection, we're going to actually start at a minimum, go up to a maximum, and back up. So this is cosine x, this is negative cosine x. Okay, your vertical reflection, you're flipping this vertically, okay? So again, we're gonna start and end, start in the middle, end at pi. This time what's gonna happen is instead of starting at a max, we're gonna start and end at our minimum. Halfway, we end up at our maximum. And halfway between each of these, we will cross our axis. Okay, so it's gonna look upside down, but also stretched out vertically and squished horizontally compared to what it would be if it was just a regular negative cosine x. Okay. Now we repeat. So if I wanted to go to the right, I would end up getting a second cycle ending at 2 pi, cross in the middle. Okay, sorry, maximum at the middle, cross in between these two, and cross in between the second two. If instead of doing my second cycle to the right, I wanted to do my second cycle to the left, I could, because it did not tell me that I had to do otherwise. So to the left, I would have to go to the left by pi. My maximum would be halfway between, so 4 boxes. And my crossing values would be halfway between those, so 2 boxes. And this was a terribly drawn cosine. I find sine way easier to draw than cosine. So please do try some questions. I have uploaded some special trig graph paper that you can print out and use. You could freehand, but just be very careful. Some of these points need to be very nice. Okay, so it should not look like a V. It should not look like a zigzag. It should be curving. Okay, and then the special graph paper, there are some that are just graphs that are pre-labeled with pi's on the axis. And then there's another set where there is no pre-label, but it does have an opportunity for you to determine amplitude, period, etc. There are 2 other kinds of shifts that we'll do tomorrow for 5.2, which is shifting left and right and up, down. Left and right is probably the hardest one, trying to combine left and right with the period change. So when you do if you pick the kind of pre-graph paper I have for you that has the characteristics, there will be some that you don't know about. Displacement and phase shift, don't worry about those today on those graph paper if you choose to use those. There's PDFs of the graph paper uploaded for you to use.